I'll give you a hint. It has something with a 2 pi on it.
At that 2 pi x of L.
2 pi f, not x of L, L, because we have x of L already over here. So 2 pi FL. So that's 2 times the pi times the frequency times the inductor. And we have it all. We have the inductor and we have the frequency. So what do we get when you do that? First person that gets, I'm just going to write this down. I'm going to start making, I can find a way to send you guys like chocolates or something like that. I don't know. Do something that's kind of, maybe not send to your house. You'd be like, what the heck is he doing? Oh, good. All right, that's, we're going to take points. So whoever gets this one faster, we'll give them, we'll start with a quarter point and we'll get you some points, extra credit tonight. How's that?
Yeah, 41.79.
41.79. I do believe that is Casey. Is that correct?
Yeah. Yeah, no.
And that is in ohms.
Ohms.
There you go. And I agree with you on that. I got it memorized from this morning. 2 pi. All right, let's do the second one. So far, it's not bad, right? There's only 8 questions, by the way. Total impedance. So they're looking for Z total here. So the first thing is you have to get X of L. So if you take X of L, and I'll give you the X of L on this one since you just so good on the other one. Whoops. There we go. .23. Maybe I should let you because I must use the same frequency as the other one. Oh, not good. If somebody wants to make sure I'm correct on that, that's fine. Okay, so we need to find Z total. How do we find, what's the equation for Z total?
Square root of R squared plus X of L squared.
Yep, X of L squared. Excellent. Jesse. Excellent. Okay. And oh, got somebody with to text it or chatted on this. 850, 855.81. 855.8. Do we get an agreement on that?
Yeah, I got 855.81 too.
Okay, good. All right, that's right here. 8. Okay, let's go on. We're moving right through this. I could have done a lecture tonight early. Not really. We have a lot to do. The other class, we actually had to go over a little bit on time tonight. We won't have to with this class. You guys move pretty good through this stuff. Phase angle. All right, so phase angle here is we're gonna do is take theta is equal to the arc tangent. If I'm moving too fast, please let me know. In this case, we're going to take X of L over R. So we have the X of L and we have the R.
I got 54.74.
I don't know how the other class we made a mistake on that degree, but that was kind of strange. How I did
It's
that.
probably because the ohms looks like 4,950. I bet I've done that on the test before.
Yeah, I see
Instead
that.
of
I need to clean that
484.
up. Yeah, I need to clean that up. That's not good. That'd be. Do you realize that if you go to 84 degrees, you realize how far that off is? So if you look at a sinusoidal waveform, that's your VN. And if you look at if it was like, this is only 54, but if it was like 84, it'd be like way out here. It'd be like totally out here. It's almost close to 90 degrees. I mean, that type of circuit's like unheard of. All right. So you got 54.74. Good. Okay. Let's go on. Any questions about these so far?
Nope.
Okay. Let's see. We're on number 4, right? No. Yeah, we're on number 4. Solve for the I total of this thing. So this is a series circuit. I'm assuming this is going to be a series circuit. So we have X sub L and we have R. So the first thing is, what's the first thing you want to do?
Find Z total.
Yep, find Z total. Because Z total is your total impedance, right? That's your total impedance. I love my job. I love this. There it is. Z total. And you just take the radical. That is the radical sign. That looks like a division sign. Yeah. All right. Let's try that again. Okay. So we take 811 and we square it plus 66.9. Nine squared. Okay. What'd you get on that?
Yeah, 813.76.
813.76.
Yep.
Okay, good. All right, we're gonna get everybody looks like we're getting extra points today. I'm writing it down. Okay, now we have to find I total, the hard part, I total, right? So that's just that. By the way, excellent job on the quizzes. And we will talk if there's any homework questions or quiz questions after this too, okay?
28.3 milli.
28 point. That's Brandon, right?
Yep.
All right, 28.3 mil. Here's the key to this stuff. You see this milli right here? Some of you, and I think it's both these classes, once in a while you forgot to put in the mils. And then you give me some real large number. And then I'm like, oops. So watch those things, okay? Watch those mils and stuff. That's 4, 5. Voltage across the inductor. I'm going to use the voltage divider rule on this. So the only thing we need to find on here is Z total. Yeah, because we got the resistor and we got inductor. We can find Z total. And then I could, yeah, let's do it that way. Let's do Z total first. Let's get Z total first out of the way. Your impedance total. So it'd just be 775 squared plus 134.1.
I got 786.52.
786.52. 2. Okay, so now I'm going to use the voltage divider rule to find VL1. Okay, so now what you do is you take the ratio, you take X sub L over Z total, multiply that by V total. So it's just, this actually reduces one step, because we would have to do is find I total, and then we would have to find VL1. So this just reduces it. So X sub L is 134.
I got 4.26.
That's about right, 4.26. All right, how we doing so far?
Good.
Good review so far?
Oh,
Okay.
yeah. Yeah, what?
All right, and that's what I want to do is I want to make sure that you're, if you have these questions, we just start hammering these things out for you and helping you. I don't want to rush through things. I'll tell you what chapters we have left to cover, and we'll get it covered. You know, if we have to, you know, use part of 16, we will. It's not a big deal. So, all right. I'm just looking at something. I want to see something here. 6. Yeah. Okay. Total inductance for a series circuit. So a series circuit total inductance is, how do you find total inductance in a series circuit?
Just add them together, right?
Yep, L1 plus L2. So you got 592 millihenry plus 1.97 millihenry. So it's gives what 593.
593.97.
0.97 millihenries.
By the way, just to give you an idea, inductors are always going to be in mils. Very, very rare will they'll be in micros. It is 99% of the time in mils. So if you ever 593.7. Okay. And you're going to find inductors quite a bit in industry. They're used for filtering quite a bit. AC power filtering to line regulation filtering and such. That's a good one.
Is that 1 divided by 1 of X as well?
Yeah, this is that 1 over. And I think I missed one here. So this one you can actually do is do L1 times L2. Makes it a little easier than that 1 over L1 plus 1 over L2. And then L1 plus L2.
Yeah, 59.36.
And this makes sense because if you look, hold on, so 59.36. Hold on. Let's check. Yeah, I was gonna say it's actually, yeah, 27. You might want to redo your math. I was gonna say
I got
59.
27 too.
Yeah, because
Yeah, I
it's
typed it wrong.
yeah. But I think once I realized that this is 29, I was looking at the 300. I thought this was 268. I was like, okay, that'd be close. But this is 29. Makes more sense for 27. Yes. So just watch those numbers on that. Okay. You're good, guys. Doing good. Thank you. Okay, how was that?
Wasn't bad.
So now you submit your answers and you get 100% on this quiz.
Yay.
See, 100% easy. No need for retakes, right?
No.
So those who are missing tonight, like Michael, you can help him with that so that he has, unless he doesn't need to help. So, okay, so far so good. All right, I'm just stretching here a little bit. Ugh. All right, let's move on for clear. I'm looking for one that I had on here that was not that one. Nope. Yeah, this one. This one actually gave me us the Exabel. Number 4 actually gave us the Exabel. I gotta take that one out. Okay, so this takes care of that problem. So what we're gonna do is move on to. We're gonna move on to. I'll show you which one it is. The capacitors and inductors, not that one. It's series inductors. So these are series and inductors and capacitors. But before we do that, any questions on homework or quizzes that we've taken so far? You want me to do any problems for you? No? We're all good to go? Okay. I'm happy if you're happy. Okay, so I'm just moving things around here a little bit. So the first thing I want to do is we're going to take care of this one. And there's a reason I'm doing it so this way. So the first thing I'm going to do is draw 2 phasors. And inductors' phasors are always facing up. Okay, just to give you some information on this. So first thing we want to do is find Exabel 1 and Exabel 2 on here. So first of all, find Exabel 1 and Exabel 2 for me. So let's see who can who want to get on this. Okay, anybody. First person that gets it gets a candy bar, a virtual candy bar. You guys at 628 for this one. And Exabel 2. $207.34, yes. Good. Excellent, thank you. Okay, so how do we find Exabels in series? Do we add, subtract, divide, multiply?
You add them, right?
Yep, and because there's no resistor in here, this is purely inductive circuit, so this has what we call reactive components only to it. So Exabel 1 plus Exabel 2. So in this case, we have 628 plus 207.
At 835.658.
Perfect.
Or yeah, you just say 66.
Yeah, that's good. Okay, I draw out the phaser. So this is going to be X of L. This is the shorter one. This is the shorter one. So this is going to be X of L2. And this is going to be the longer one, X of L1. So you notice that if we take these two phasers and we add them together, we get your X of L total. So that's how you get X of L total. They're not pointing in the opposite direction. In other words, down 180 degrees. If they were, we'd have to subtract them. They're facing both facing up. It's great. We don't have any resistive components, any passive components on here. We just have some active components. So there's no need for trigonometry on this. So the phase diagram is up there. So I can actually find the voltage. Let's do the voltage of X of L1. So VL1, using the voltage divider rule again, I could do L1, which is 628. 628.310. And then if we take that and divide that by 835.6.
Now like 3.
Yep. 3 volts. And we gave about 3 volts. So that means this other one has 1 volt to it. That's it. This one has 1 volt to it because it's total of 4 volts. Pretty straightforward, right? For that one?
Yeah.
Yeah. So this is just practice, but I'm showing you why there's a reason behind my method and my madness here. Okay. You just have to work with me on that. Okay. So second one, let's get the second one. And let's do the second one here. I'm just going to move this guy over. Move this guy. I'm going to move that guy down so I can use some space here. Actually, move them up. All right, so this is pointing up. Which way do capacitors point? Up or down?
For the second one?
Yeah, for the capacitors, yes.
Looks like up.
Okay, we add it up.
Oh, they go down?
We do it down because of the ground.
Okay, because we're dealing with capacitors, and capacitors are always out of phase with the out of phase. They always lag behind the source voltage. So these guys will be pointing downward. And remember, they're a negative component. Whoops, you don't want to do that. You didn't see this extra one right here. Let's try that again. Okay, so we have these. So we have to find X of C1. Get that down there. So X of C1. And the equation for X of C is 1 over 2 pi FC. So let's find X of C1. Let's call this X of C1, and we'll call this X of C2. Two pi, whoops, got the 1,000. Times that by 0.47, my keys. 338. And what's X of C2? Since I did the first one, somebody give me the second one.
We got 482.29.
All right, so remember that total capacitance capacitor reactance in the circuit, this is series, so we have X of C1 times X of C2. Correct me if I'm wrong on my equations. Over X of C1, X of C2. There, that's better. And that should give us X of C total.
At 964.58.
All right, that sounds a little too high.
Yeah, it does.
You added them. Sounds like you added them.
Yeah, I times the top and then added the bottom.
Okay, let's do that again. Let's see what happens. Let's see if you're okay. Let's be try to 8.627. By the way, I sent your stuff into Professor Brown.
Oh, cool. Thank you.
You're welcome.
Got 198.94,
198.94. Is that correct?
yeah.
Yeah, I didn't put the parentheses when I divided. That's what I did wrong.
You don't know how many times I've done that when I was making your tests up. All right, so this top part is already. This top is the phasors, the phasor diagrams. So that's done. Voltage across the capacitor. I'm just going to use that the voltage divider rule on here again, and I'm going to do is put in what's what voltage across. I'm just going to do X of C1. And that's it. X of C1 divided into X of C total. Times it by B total. So if we do 338.627, 338.627 divided into 198.
6.8.
6.8, you said?
Yep.
0.8 volts peak. Yep. So what, how much the voltage would, wait a second, is that correct? Something doesn't seem right. Hold up, something doesn't seem right here. Can we get more voltage than we have in there?
Yeah, I'm getting 2.82.
2.82. That sounds better. Let me see what it does. Let's see, X of C1 over X of C total. So 338. Divided into 198.4. Something go wrong here?
I keep getting 6.8.
Yeah, I did too. It can't be. What am I doing wrong here?
You got to multiply it by 4, right?
Yeah, I multiplied by 4. Something's not right. Let me see if the equations I used are incorrect. Let's see. First thing that's coming to my mind is not adding up. Series.
X of C total wrong?
X of C total.
Yeah, shouldn't we just add the x of c1 plus x of c2?
I am thinking we are off on that part of it. I might have my equations messed up on.
Our formula for x of c total is that right?
X of C total should be 1 over X of C1 plus 1 over X, 1 over X of C1 plus 1 over X of C2. That's for parallel. We're in series. It should be X of C1 plus X of C2. We are wrong.
Yeah. Yeah.
Wow. I made a mistake. Okay. My boo-boo. All right, let's backtrack. That's why we have to check each other's equations. All right, let me get that corrected. I thought something was off, didn't look correct. So this is just, somebody, who said it was supposed to be X of C1 plus X of C2 in the beginning? Was that you, Brandon?
Yeah, it was Brandon.
Okay. Brandon, you were right. You get some major kudo points. I don't know how I'm going to give you points, but we'll give you some points.
Virtual candy bar.
Virtual candy bar, there we
Virtual
go.
Reese's Easter egg.
Man, I don't know how much you guys have missed all that candy.
Yeah.
I'm dying right now.
Those added together is 820.917.
820.917. That makes more sense. And then this guy's going to be, I think this guy's going to be about 2.82, if I remember right. So this is going to be, I did X of C1, right? 338.627 divided into X of C total, which is 820.
I got 1.64.
I got the same.
1.64.
Yep.
Thank you. And 1.64 volts. Okay. Let's see if that makes sense now. X of C is smaller than that, so we know X of C2 will be larger. 1.64 sounds like it's reasonable. That means we would have approximately 1.64 minus 4. We're going to have approximately 2.36. And if I remember right from this morning, 2.36 is equal to X of C2. Remember, we don't have to do the trigonometry in here because we don't have a tacit component in here. We don't have to worry about that. Does that make sense? Besides me making mistakes on capacitors? You know, I was thinking, to be honest with you, what I was thinking was not capacitor reactance, but I was just thinking total capacitance. Total capacitance in a series circuit is that 1 over 1 over. That's what I was thinking. But again, I make mistakes. All right, anybody have any questions on that?
Nope.
Can you give me a thumbs up or a okay or a I'm good, whatever it is on your chat? Just say I'm good. Okay. Jesse, you okay too? Oh, by the way, I did try to rebuild the circuit and then take some measurements on the for parallel that we did last week. And the scope was giving me about 10 degrees off. And I went out and I got, went back to campus, I got a 10 ohm resistor. And then I did some measurements, but I was still getting way too much. 10 degrees is way too much. So I'm still working on those little dilemmas with my equipment. All right, so we're done with that. Any questions in regards to this part of it? Because when we get into the next part, it is important that you, when we actually apply the phasor diagrams, you can actually see what we're doing on here, okay? And by the way, this was in chapter 23, because we're in chapter 23, and this was like 23-1, 23-1, trend 23-2, and 23-3. We'll do parallel next week. So I'm going to move to our second little equation. This one I'll start typing out a little bit more for you. This guy. Does anybody need a little break? Thumbs up if you want a break. Okay, the first thing I want you to do is take a look at this circuit. What do you see that's unique about this circuit?
Got a resistor, a cap, and yeah, it's got all three.
It's got all three. So it has two active components and a passive component. Two active components, that's why we call reactive, it's active. That's L1 and C1. This is an RLC circuit. This is the most common type of circuit that you'll see when it comes to applying filters, because a lot of times in a filter circuit, you'll have two active components and a passive component. So what we call reactive-active is the same thing. Okay, so the first thing I'm going to do is say to you, ignore this R2 at this point. Just ignore it. Okay? First thing we're going to do is we're going to draw that phasor diagram. So X of L's, do they point up or down?
Up.
They do point up. I'm just moving so I can make bigger room here for myself. Okay, they do point up. And I'm going to make this one green. So X of L is going to be green. And I noticed that the X of L1 is smaller than the X of C. So I'm going to try to keep it as best I can, just like that. And then, which way does the X of C point?
Down.
Down.
Down, yes. Okay, so we have one pointing up and one pointing down. So I'm going to do is, I'm going to copy these guys, Control C, Control E. It's going to move things over. I'm going to make this a little bit smaller too. I don't want to take up all my room. Okay, there's that one. So we have these two. So X of L is pointing upward and X of C is pointing downward. What we call the net resultant, the net resultant on here is going to be, in this case, we have to subtract X of C1 minus X of L1. Because there are two vectors that are pointing in the opposite directions. So what do we get for this when you actually subtract these two off?
I got 1408.51.
1408 point what?
51.
Okay. So is that going to be capacitive or is it going to be inductive? That's the question we have to ask. So the way to answer that question is you have to look at which reactance, boy, I can't speak, reactance is larger. In this case, it's the capacitance. So this is going to be 1408.51. And it's going to be capacitive, and it's going to be a capacitive circuit. Does that make sense to you guys? I want to know if I lost anybody at this point. Good. Manuel, how you doing? Okay.
So you're saying if you can get a negative number in this if X of
Well-
L is bigger?
Well, let's talk about that right now. Since let's see, Jesse. I think Jesse. Alejandro, you okay too?
Yeah, I'm good.
Okay. All right. Good. I just wanted to make sure. Okay. So in all honesty, we don't want to be dealing with negative ohms because that's 1408.51 ohms. Don't always look at the arrows pointing downward and the arrows pointing upwards as being any negative numbers. Just take and subtract off. So let's say if X of L was larger, just make sure that you don't have anything. So you do X of L minus X of C. In this case, we have our X of C larger. We just subtract X of C from the X of L.
Okay, so you can change which one comes first then.
That's correct. Absolutely.
Okay, cool.
Absolutely. If you start getting into negative numbers, that starts getting into some really strange areas of electronics. And it does. There is negative numbers and resistances. You can't have them. So. Okay, so what we're going to do is I'm going to redraw the circuit because now it looks like, and I'm going to redraw it to see if I can redraw this. And I'm going to do Control C, Control V. All right, so I'm going to try to do is move all this stuff up just a little bit. All right, so what I'm going to do, and this is where I have to take things out of here. So first of all, it's not inductive anymore. This is part one of what we have to do. And we're just going to redraw the circuit. Whoa. So we have the new circuit. So new circuit is going to look like that, but this is not going to be a 10 nanofarad anymore. In fact, we're going to have to find the value of this. Let's call this, instead of, let's label this, let's call this, net X of C. So I'm going to call it C net. Now we know that a C net has a capacitive reactance of 14.08 ohms, because we did that already. We solved that already. So we have that. So this is going to be X of C net is going to be 14.08.5 ohms. So to find the capacitance value of this, we have to do is do some math. Yes, we love math in this class. So in this case, if I do C is equal to 1 divided into parentheses 2 times, I'm just going to write it out, 3.1415 times our frequency, 6K hertz, times it by our X of L, or X of C, sorry, X of C, which is 14.08. 14.08. And I'm going to go ahead and bring the smaller numbers here. So let's figure out what we have here. And let's get a value. What do you get for that?
Is it going to be super small?
Yes, it is.
Okay. Well, I'm counting the zeros. It's like 19 that U.
This, how about this one?
Oh, nano. Yeah, I even got like 19 nano.
Yeah, you can go 19 on this if you just rounded up that 18. You have 1.8 e to the minus 8. It actually comes out to be about 18.83 nanofarads. A really small capacitor. Really small capacitor. You know, this circuit reminds me more of a communication circuit with the capacitor so small. So, yeah. Did I lose anybody on that?
Yeah, you lost me in the last part.
This part right down here?
Yeah, that part
Okay.
right there.
Okay, so basically in order to, so what I did is, and I'm going to, I got to get rid of these vectors. I'm going to have to, there's no way I could do this. I'm going to have to get rid of these two vectors. They're moving around, boink, boink. So there's my, I'm just going to move things around here, okay. So you agree that I had to find the net resultant of this circuit. You
Yeah.
agree with that? Okay.
Yeah, I got that
That's
part.
that's this part right up here.
Yep.
Okay. So coming down here, so what this tells me is a capacitive circuit. So this is X sub C. So this is going to be, maybe I should have put, this is going to be X sub C net. And I'm going to move it over so you guys can see it in a second. I'm just cleaning up all my handiwork here now. Where'd it go? There it is. I'm just getting things cleaned up. That's all I'm doing here. Okay, so basically I have these two. There's my net resultant. I take this, and this comes to be X sub C net, which means it's a capacitive circuit. That means it looks like this down here, okay?
Mm-hmm.
So what I did is, I wanted to know this value of this capacitor. I already know it's X sub C, it's capacitive reactance. It came out to be 14.08510. Using that same equation we had, before, 1 over 2 pi F C is equal to X sub C. What I did is I did some algebra, and I said that 1 over 2 pi F, now X sub C are going to change. X sub C is equal to C. And this gave me, now I can find the capacitance value. Do you want me to do the algebra on that to show you?
Yes, please.
Okay. So first of all, I'm going to multiply this side by C. I'm going to do that. I'm going to change some colors out here so you can see what's going on. So I'm going to multiply here by C. So that goes away. If I do that on this side, I have to do it on this side, right?
Yep.
Okay. So there's the C. Now what I have here is 1 over 2 pi F is equal to X sub C. Well, I want to get rid of C now on this side. So I'm going to do is I'm going to do my math, and I'm going to do is divide by C on this side. I started X sub C on this side. Sorry, X sub C. That was so good. I was doing so good. So I'm going to do is I'm going to divide by X sub C on this side, which cancels out over here. Well, if I divide on this side, X sub C, I have to do it on this side. So that just becomes X sub C on this side. So what we're left here is 1 over 2 pi F X sub C is equal to C. That help you?
Yep.
Good. All right, so can I erase my math over here? Or do you want me to keep it up for a little bit?
I'm good.
Okay. All right, so let me clear up this, clear up my drawing. So we found this to be 18.83 nanofarads. Now it looks like a circuit now. So we got my X sub C, we got all the capacitor value. And by the way, an 18.83 nanofarad capacitor, there is none out there. I would have to look it up, but I think you could get, I think what the closest we could get is an 18 nanofarad. I think there is an 18 or 20 nanofarad capacitor, but you could have one designed, but up to you. All right. So this looks like a passive circuit, right? So we have X of C net, and we have R. So what are some things we can find on here? How about Z total? So this is just R1 squared plus X of C. I'm going to call it net squared. Okay, tell me what that gets for your impedance total. By the way, what are some negative effects of having some mismatching impedances on your circuit? Could possibly happen. You can actually draw more current into the you could draw more current into an antenna. So let's say you had an antenna hooked to the circuit and it did look like this, and you didn't have impedance matching. Yeah, there could be a little bit of a problem with your loads.
For Z total, I got 1727.39. I might as well say 0.40. 1727.40.
1727. Okay, I'm going to type this out instead of this because I'm going to give it to you guys. I'm going to clear this. I'm just going to type it out. Okay, so I'm going to do is type. Oops, I didn't want to do that. Control C. Think I undo. Okay. So Z total is equal to SQR of R1 squared plus X of C net squared. And that gives you, how much did you get?
At 1727.40.
So it's just taking these values that they just did on there. Any questions on that? I total. This is the most important right here. I total is probably the most important on the circuit because we're going to take this I total and bring it back to our original circuit. We'll be there in a second on that. So I total is equal to V total over Z total. And by the way, if you actually did come up with an 18.83 nanofarad capacitor, or you found one and you built this circuit, this is what the generator is actually seeing. It does not see the inductor and the capacitor, but it sees this circuit right here. So this is what we call an equivalent circuit. An equivalent circuit. All right, so V total is 10 volts peak divided by 1727.
Yeah. 5.79 milliamps.
5.79.
Isn't it only 5 volts peak because it's 10 volts peak to peak?
Oh, I'm using peak. That's right, it's peak to peak. Thank you. There we go, peak to peak. Did I use any more? Did I use anywhere else? Was peak, not peak to peak? Okay, I'm fine. Yeah, it would be 5 volts peak. I think I'm okay so far. This is the only place I did it. Okay, good. So we're keeping all the values, and this is 9 milliamps, and we have to put peak to peak on here too. Let's see if I'm dropping this font. I can't drop it anymore. Let's see if I can move things over. It's not going to let me. I'm going to try to sneak this guy. I'm going to try to sneak this guy. Up a little bit here. All right, there we go. I'm going back to it so you can see it. Okay, we're good to go. All right, any questions so far?
Nope.
All right, C total. Let's find, let's solve for, we don't really need to solve for C net, voltage across C net. What we're going to do is, and I'm going to go ahead and bring, I'm just going to bring this back. You'll see what I'm doing here. See in a second. What we're going to do is bring this total current. Actually, we have one more thing to figure in here. That is the phase change on here. We got to do that. All right, so we do have one more. That's the phase change. Phase change is going to be equal to, that's the theta. We'll use that as theta is equal to inverse tangent x of c net divided into R1. I'm going to make sure that I'm correct on that. I'm good to go. Okay, for this one, what do we get for theta? And what do we get for the phase change on it?
54.6.
54.6 degrees. Did I lose anybody on this? What's important, like I said, is this 5.79 milliamps. And I'm going to, so you don't get that confused. So this means that the circuit is capacitive and it's lagging behind by 54.6 degrees. It's not too bad. So what we want to do is take this 5.79 milliamps and we want to put it back into the original circuit. So the original circuit now actually sees right here. I'm just grabbing something so I can type it out. So right here, this sees I total is equal to 5.79 mils. I'm going to put that in a different color. I just want to get a color on it. That's really good. Let's go blue. Okay. So now what we can find on here is the following. So that's why I left it. See, IR, VR1, VR2, VR2, yeah, VR2, VL1, and C1. So in this case, we're just going to use Ohm's law, IR relationship. So 5.79 milliamps times that by 1,000 ohms gives me approximately 5.79 volts. Okay, you guys do the ones for VL1 and VC1.
For VL1, I think I got 7.2 volts.
Sounds good. That's you or Jesse or somebody else. Can you tell me what you get from EC1?
I got 15.36 volts.
For X of C1?
Yep.
I'm going to check that.
It was 3.6.
Yeah, I actually got that too. Seems a little high, but
It is.
it's the same. It's the same I got.
So we did 5.39 times that by, hold on, 5.79, sorry.
Yeah, 5.79 milli times that 2652.58.
Yeah, that's 2.35. Let's see if it ever comes up. Let's see what happens. I can't remember them this morning on this one. So if I take the two active components and add them together, and I do that, gives me 22.64. Maybe something's off on our current. We'll find out in a second here. I'm just checking. I'm doing a math check on this. Yeah, it's way off. Did we make a mistake on here someplace? 5.79 mil. I'm looking. Let me make sure that 10 nanofarads is correct. X of C1. Two 262.58. Just give me a second. I'm going to rerun that math one more time on that. 2652.58. 5.79 e to the minus third times that by 2652.15. Why am I off? Oh, I'm correct. I'm correct. I'm doing something else wrong. 15.35 minus 7.29. Subtract them. That's 8.06. There we go. Okay. I see what I did wrong. That looks correct. Hold on. I'll tell you in a second, guys. I'm going to tell you. What's the voltage on that? 5.79 squared plus parentheses, 7, oops, we don't want to do that. We want to do 5 minus 7.29. Here we square it. 9.92. It is correct. Okay. It is correct. Everything's correct. Get a little tired and your brain starts going in the wrong direction. So basically on this numbers aren't correct. So remember that we are dealing with two reactive components, okay? Two reactive components. That means that this one has 15.35 volts and this has 7.29 volts. So if we subtract these two voltages, and I'm going to put the equation to check, let's show you what the equation looks like. We call it a check. And I just was not, what I was not doing was subtracting. So we take the square root of parentheses, and I'll put the diagram up so you can see this. We take R1 and we square it, plus, and this is going to be, sorry, VR1, and square it, plus parentheses. Now we have to take VC1 minus VL1. And then we square that. Now, if you do that, you get approximately, because we did not have 9.924 volts. We did not go out too many decimals on it. So if we do that, that comes out to our source voltage. So this is actually equal to the total. How many people did I lose on that one? They put you guys up. Thumbs down. Did you see what I'm doing here for a check? Thumbs up if you do, or that's I want to see some questions on what I just did. Okay, good. Sometimes I have to get my mindset on where we're in active or we're in what kind of components we're doing, because I just moved from inductive to now capacitive inductive resistive circuits. Alejandro, you okay with that? Casey, you're good. Okay, it's good. All right. Anybody have any questions on what I just did on this? So basically on this type of circuit, what you have here, and we're going to throw the simulator on here to see what the current is in a second, is that we have an RLC circuit, and I'm going to have to move some stuff around. I'll have to put some instrumentation on here, but we can move things around. And we have three components. We found this to be a total of, found to be a capacitive circuit. And based on using our previous experiences, we came up with some phase changes and all that on here. We also came up with the total current, which was 5.9 mils, 5.79 mils. And then what we did is we took this current and we moved it back over here. So let's run this thing and see what happens. So what I want to do is I'm going to put some meters on here. And it's not going to let me put that right there. I'm going to toss. I'm going to have to rotate this guy around. Okay. Get rid of him. Clamp on him. Amps. Voltage. AC voltage. Okay, good. So let's check to see if the current is correct at least. 2.0592. Okay, this is RMS. 2.059, 2.0. Check here, check to see if everything looks good. Times it by 2. 5.82. I get 5.82, and they got this meter's saying 5.82 volts peak to peak, and we came up with 5.79. I think we're good to go on that. Anybody disagree on that? Okay, let's check the voltage at, I'm really curious to see what the voltage at the capacitor is. So I'm just going to put another meter right here. And I could hook it up to the, I could actually hook this up to the scope, and I will do that in a minute too. So volts AC. Remember, this is an RMS, so we got 5.443 times it by 1.414 times it by 2, 15.39. Yeah, it looks good. So it looks good on that because we came up with 15.35. We're right in the money. Looks good. Sometimes having big numbers, it gives you a little bit, gives you the scares, but looks good. Okay. Let's put this hooked up to an oscilloscope to see what happens. Let's see what's going on with it. That's the fun stuff when we play with the scopes. Do a 4-channel oscilloscope. Let's go Textronics, Agilent, Textronics. I like the Textronics scopes. They're much easier to use. Okay, first thing I need is ground. Control-C, Control-V. And then I'm going to do is take channel 1 and put it, do I want to do it right there? Yeah. So I'm going to see if this comes up. I want to see if I can come up with VR2 real quick. So I'm going to do is to stick these probes in right here. So it just gave me my probe here, that probe there. Turn the scope on, run my circuit. Tells me that these two are running. Powered on, auto set. Let's try the auto set one more time. Doesn't like that. See if we can get this thing better. There we go. Okay, I'm going to rise these two up to meet in the middle. Whoops, right up the middle. And I'm going to pick it up so you guys can see this. There's a phase change. I like that one. So you can see there is a phase change between the two. Let's do some math on here. Let's do some measure, and I'm going to do is I'm going to see if I can remember how to use the math. So I'm going to do a subtraction. I'm going to do a channel 1 from a channel 2. I'm going to do channel 1 is going to be voltage. I passed that peak to peak. There we go. So it's 9.09. So that's our 10 volts peak to peak. And then our channel 2. Channel 2, measure. Channel 1 is right there. Channel 2 is going to be voltage peak to peak. But this time you notice it's actually 6.83. Look what I have right here. Remember, I have it right here. So if we actually take and move this down, what did I come up with? 7.29 minus 15.3. Somebody take the math and do that for me and tell me what you get on that. Jesse, can you subtract the 2 for me, please?
$8.06.
8.06. If you look at this, where was the math at? Let's do the math. There's that, there's that. I'm going to do a measure. If you look at channel 2, we got 8.12, and you see 8.06, which shows that when I put because that's across these two right here. So it's subtracting these two voltages, this voltage from this voltage, that's that. So if I do the math on here and channel 1 from channel 2, let's do that. We are getting, both these are set voltages. We're getting approximately 2 point something. Let's do the measurement. Let's do channel. Hopefully it'll come up with, we won't come up with it. Let's see if I can get that. I'm trying to get the math on here. Yeah, channel 1 from channel 2. It gives me it right here. I was looking to see if it actually gives me the value, but we can actually calculate this. We get 2, because each one of these set the channels is set for 2 volts per division. Yeah, it's set for 2 volts per division. So if we look at this, we have 2.5 plus 2.5 is 5. 5.79, yeah, 5.79, 5.79 volts. So that's how I get the voltage across that that resistor. Now you're probably asking yourself, well, could we also take the probe and put it from here, subtract, let's say we subtract, let's say we put one probe here and then we put another probe here. So if we take the voltage at this point and we subtract it off from here, well, that gets a little bit tricky because you're trying to take the passive component and subtract it from a active component. Let's see if we get the phase change on here. Let's see what we get for phase change. I'm curious. It won't give me on this one. But let's see if we can actually do some, let's see if I can put display. There it is. So you can see using this type of graph that you actually have some sort of phase change, and it's about 54 degrees. It's about 54 degrees. So that's just go back. That's actually taking in this value and this value. You have to keep these two voltage at the same level. So we did pretty good on this. Okay, give me a thumbs up if you're good, or put in the chat that you're lost, for L for lost. Emmanuel, did I get your question answered? Or am I not hearing anybody? Can everybody hear me?
Yeah, I can hear you.
Okay. Emmanuel, did you?
Oh, people, yeah, he texted or he typed. He said he got it figured out.
Okay, got it. Okay, I apologize, Emmanuel. All right. How are we doing? Do you want to go out to parallel tonight, or do you want to hold?
It's up to them. I'm gonna be leaving here soon.
I know that two of you have to go. How about Jesse and them? Do you want to continue on with this a little bit with parallel, or do you want to hold?
Yeah, I may have to go pretty soon too, Mr. Charles.
All right. Jesse, do you want to, what do the rest do you want to do? Here, let me do this. Let me see if I got a poll for you guys. I'm going to send this out to you, these diagrams out to you. So I'm going to shut this off. And I'm going to do